This video will show you how to size a rupture disc installation using FlareTot. When sizing a rupture disc, the entire installation is examined, from the inlet vessel or equipment, to the atmospheric vent or outlet flare header. The installation is considered adequate when one of two conditions is met. 1. The calculated flow rate for the installation is greater than the relief flow rate when the inlet pressure is at allowable overpressure. 2. The inlet pressure is less than the allowable overpressure at the required relief flow rate. Both criteria are evaluated in FlareTot, depending on which calculation method is used. Rupture disc calculations can be contained in network rupture disc sources or standalone calculations. We will first show you how to create and access a source rupture disc calculation. Then we will carry out a detailed standalone calculation. To create a network rupture disc source with an associated calculation, we first need to change the source to a rupture disc. Note that we have used the tutorial 8 FlareTot file provided. First, open the source properties by double-clicking on it in the network drawing. Now change the source type to a rupture disc. The source symbol changes to a rupture disc, and the rupture disc calculation page is now visible. This rupture disc calculation page is the same as used for standalone calculations. The only difference is that some parameters such as tags and design conditions are shared with source properties. Now we will create a standalone calculation and complete the rupture disc sizing. We first need to add a standalone rupture disc calculation. Click on the Rupture Disc Calculations button. This opens the Rupture Disc Standalone Calculation Manager. Click on the Add button to add a new calculation. The calculation is identified by the Rupture Disc tag, which has not yet been defined. Double-click on the calculation in the list to define and calculate the installation. We are now ready to define the details of the rupture disc installation. Our example rupture disc installation protects a vessel with a design pressure of 12 bar gauge. It is designed to ASME 8 code. As allowed by this code, the installation has both a main and a supplemental rupture disc. The main rupture disc protects against process overpressure, while the supplemental disc protects against exposure to fire. First enter the installation descriptive data and the design pressure. The defaults for the design code and disc arrangement do not need to be changed. These default to ASME 8 and single set pressure. Now we define the rupture disc installation arrangement from the piping layout. In a study phase, this would need to be estimated based on preliminary equipment and flare header locations. This drawing shows the dimensions of the rupture disc installation. Note that it is also included with the tutorial documentation. First define the main rupture disc arrangement. Go to the main rupture disc page. New calculations have a default arrangement. This arrangement can be changed to the required layout. The default consists of a vessel entrance, a vertical pipe, rupture disc, another vertical pipe, a standard 90-degree elbow, and a horizontal pipe, which connects to a header. The entrance, exit and rupture disc are required and cannot be deleted. Enter the vessel tag in the equipment tag field. Now set the corner radius by clicking on the corner radius options. The vessel exit is rounded, and has a corner radius to pipe diameter of 0.02. Select the connecting vertical pipe. We have overlaid a reminder of the pipes section that this represents. As a preliminary estimate of the installation size, we have selected 3-inch. Select carbon steel as the piping class. Set the nominal diameter to 3-inch. Our pipe class gives this as Schedule 80. Finally set the length to 1.5 meters. Select the rupture disc. The default coefficients for the coefficient of discharge and velocity head loss methods are used for this demonstration. Manufacturer values should be used if available. The rupture disc diameter will be set from the connected inlet pipe, which is the default. Select the next piping element. Complete the details as before. For this, and remaining pipes, the piping class requires Schedule 40. The fitting in the default arrangement is a 90-degree elbow. We need to insert a vertical pipe and T-fitting with flow through the run of the T. Click on the Add Fitting button to add a new fitting above the pipe. Change the new fitting type to a T with flow through the run. Change the nominal diameter to 3-inch. The default NC class of 150 pounds does not need to be changed. It will be used to calculate the inner diameter. Now add a new pipe above the T by clicking on the Add Pipe button. Set the pipe data as before. A new pipe defaults to a horizontal orientation. Change the inclination to a vertical upwards pipe. Note that the symbol in the list changes to indicate the inclination. Select the next piping element. This is the 90-degree elbow, added by default. Change the size to 3-inch. Select the next piping element. Complete the details as before. Select the next piping element. Enter the maximum pressure expected in the flare header at the tailpipe entry point. This is 1.5 bar in our example. Also, set the optional description. The installation has a supplemental rupture disc for fire, so tick the supplemental disc checkbox. The supplemental fire disc arrangement page is activated. We now define the supplemental rupture disc arrangement as before. The arrangement is shown above for reference. To proceed, we need to add the sections shown above, namely, a T-exit, a vertical pipe, an elbow and a horizontal pipe. Click on the Add Fitting button to add the T. The new fitting defaults to a 90-degree elbow. Change this to a T, with flow through the branch. Set the nominal diameter. Now add the vertical section of pipe by clicking on the Add Pipe button. Complete the details as before. The default for a new pipe is horizontal. This section is vertical, so change the inclination to vertical upwards. Now add a 90-degree elbow by clicking on the Add Fitting button. The fitting type defaults to a 90-degree elbow, so only the nominal diameter needs to be changed. Add the final horizontal pipe by clicking on the Add Pipe button. Complete the details as before. Finally, select the header exit. Set the outlet pressure to 1.5 bar. Both the main and the supplemental rupture disc installations are now defined. Now the sizing relief cases need to be defined. Open the Relief Case Properties page by clicking on the Case Properties tab. By default, the calculation already contains one design case, which is undefined. The normal flow conditions, to the vessel, are shown here. This data is also provided in the tutorial documentation. For our example, we have two relief load sizing cases. There is a process blocked-in case, with only the vapor flow to be relieved. Properties for this case will be manually specified. There is also a fire case. The properties for this case will be determined using a fire relief calculation. Flare Tart will automatically use the process case to size the main rupture disc, and the fire case to size the supplemental fire disc. First we define the process case. Enter a description. Set the case type to process. This ensures that the conditions at relief will be calculated at 10% above the design pressure. Enter the vapor mass flow. Enter the temperature and pressure at normal conditions. The actual temperature and pressure at relief conditions will be calculated from these values, using constant enthalpy. Enter the composition of the vapor. The process case is defined. Now add a fire relief load calculation by clicking on the Add Relief Case button. Ensure the fire calculation is selected and click OK to create the calculation. The default vertical vessel type and ellipsoidal heads are OK. Enter the inner diameter and tan to tan height. Select the Fluid Properties page. The normal operating conditions in the vessel need to be specified. The conditions at rupture and relief overpressure are calculated from the normal operating conditions, based on constant volume with heat input. Enter temperature and pressure. The vessel has a hydrocarbon liquid normal operating level of 1 meter. This affects both heat input and time to reach rupture pressure. Click on the liquid present checkbox and enter the liquid level. Now enter the total fluid composition based on the fluid flow to the vessel. Click the flash button to flash the fluid and display the vapor and liquid compositions. This is not required for the calculation to proceed, but is provided for information only. Now select the Calculation Options page. Select the Advanced Relief Load model. This model calculates heat transfer coefficients for wetted and dry areas. Enter a vessel wall thickness of 20 mm. The default thermal conductivity is acceptable. Click the Calculation button to calculate the relief load. The results page is shown. Note that in this case, the design or rupture pressure is reached in 41 seconds. Results can be printed, saved or copied to the clipboard here. Close the results page. Save and close the calculation, which sets the relief load properties in the Rupture Disk Case Properties page. Select the Rupture Disk Calculation page. Select the Calculation Options page. Both the coefficient of discharge method, termed KD, and the velocity head loss method, termed KR, are selected by default. The KD method only rates the rupture disk as a nozzle, and does not model the surrounding piping. The method is approximate, and only applicable for certain piping arrangements. We do not use it here. Therefore, deselect the KD method in the sizing calculation methods. Select the KR Options tab. This page gives the methods used to calculate the pressure drop over the rupture disk and piping. The default options do not need to be changed, but so you understand their usage, we will discuss them briefly. Firstly, more than one method is allowed for a given phase, so results can be compared. Also, a method is only used if the fluid phase matches the method. For example, the incompressible method is only used for liquid fluids. The API method is not selected, as it is approximate, for example assuming a specific heat capacity ratio of 1.4. Use it only if required by project standards. The LAPL method uses analytical, adiabatic equations, and a calculated specific heat capacity ratio for each section. It is fairly accurate and convenient for vapor phase fluid, as it is much faster than Dyer's. Finally, the Dyer's method can be used for all phases, including two-phase, vaporizing liquid and retrograde condensation. Dyer's is the most accurate method, but will take the longest to calculate. The default two-phase hold-up methods represent the most conservative, that is, using calculated hold-up for inclined upward pipes only, and no slip for other inclinations. Now run the installation rating by clicking on the Calculate button. The sizing results are shown in a new window. The main rupture disk installation is rated using the process blocked-in case. A small amount of liquid is produced when the vapor is compressed to relief overpressure, and thus the Dyer's method is used for rating. The calculated pressure in the vessel exceeds maximum allowable, and thus the installation is undersized. The supplemental fire rupture disc installation is rated using the calculated fire case. The fluid phase is vapor, so that both the lapel and the Dyer's method are used for rating. Both methods show that the pressure in the vessel is less than allowable, and thus the installation is acceptable. There is close agreement between the two methods. After closing the results form, you can view the pressure profiles across the installations to determine if there are any bottlenecks. The maximum allowable relief overpressure and the pressure profile calculated using Dyers are shown. It can be seen that the pressure exceeds allowable at the T-fitting. Note that, if optional tags, such as pipe tags, are set, they will be displayed instead of the item label. Now display the supplemental rupture disc installation profile. The profile for lapel and Dyers are very similar. The pressure is always less than allowable, so the installation is acceptable, and possibly smaller piping may suffice. We now revise the installation piping, nominal bores. We will change the main installation from 3 to 4 inches, since the pressure drop is too high. In addition, we will change the supplemental installation from 3 to 2 inches, to see if this meets the required maximum pressure. This is also the smallest size we are allowed in our project spec. First, change all main rupture disc elements to 4-inch. Now change the supplemental rupture disc elements to 2 inches. Remember to change the shed piping section to 4 inches. Click on the Calculate button to rate the installations with the new sizes. Now both the installations are acceptable, since the calculated vessel pressure is less than allowed. The final installation is shown here. This completes the rupture disc tutorial.